Maximum Product Subarray. Here's a question that separates the good from the great. Maximum Product Subarray looks easy, until you hit those negative numbers and zeros. This Pattern Mastery 100 staple pops up at companies like Google and Amazon, and it's famous for tripping up even seasoned coders. If you can nail this one, you'll show interviewers that you're not just following patterns, you truly understand array dynamics and edge case thinking. Let's unlock the secret together. Let's break down the challenge. Given an integer array, your job is to find the contiguous subarray that has the largest product. Unlike some problems, multiplying negatives can flip the result, and zeros reset your progress. That's why this problem is sneakier than it seems. Now let's assess our options. A brute force approach would try every subarray and compute the product, on squared or worse, but we want on time. The trick is to keep track of both the maximum and minimum products ending at each index, because a negative number could turn your lowest product into the new maximum if multiplied. As we scan, we update both, and always check for zeros that reset the product chain. Here's the structure of our solution. First, initialize three variables. Max_prod for the global max. Cur_max for the current maximum product ending here. Cur_min for the current minimum, for handling negatives. Then, start all at the first element. Next, for each number in the array, starting from index 1. If the number is negative, swap current maximum and current minimum. Update current maximum as the higher of the number itself or number times current maximum. Update current minimum as the lower of the number itself or number times current minimum. Update maximum product if current maximum is greater. And lastly, return maximum product. Now let's try to implement it using solution 1. We're defining a function called maxProduct that takes an array nums. We store the length of the array in n. We create two arrays, maxDP and minDP, both of size n, filled with zeros. MaxDPI will store the maximum product of a subarray that must end at index I. MinDPI will store the minimum product of a subarray that must end at index I. This matters because a negative times a negative can become a large positive. We set maxDP 0 to num 0. We set minDP 0 to num 0. Because the only subarray ending at index 0 is the first element itself, we create result and set it to num 0, because that's our best product so far. Now we loop from I equals 1 up to n-1. Inside the loop, we store the current number in x. If x is non-negative, then multiplying by x keeps the order of max and min the same. So maxDPI becomes the maximum of x itself, or maxDPI minus 1 times x, and minDPI becomes the minimum of x itself, or minDPI minus 1 times x. If x is negative, then multiplying flips things. A previous minimum could become the new maximum, and a previous maximum could become the new minimum. So maxDPI becomes the maximum of x, or minDPI minus 1 times x, and minDPI becomes the minimum of x, or maxDPI minus 1 times x. After that, we update result by comparing it with maxDPI. When the loop ends, we return result. Time complexity is O of n, because we scan the array once. Space complexity is O of n, because we store two DP arrays. Let's verify solution 1 for maximum product subarray. Input is nums equals 2, 3, -2, 4. We start with maxDP0 equals 2, minDP0 equals 2, result equals 2. At I equals 1, x is 3, which is non-negative. MaxDP1 becomes max of 3 and 2 times 3, which is 6. So maxDP1 is 6. MinDP1 becomes minimum of 3 and 2 times 3, which is 6. So minDP1 is 3. Result becomes max of 2 and 6. So result becomes 6. At I equals 2, x is -2, which is negative. MaxDP2 becomes max of -2 and minDP1 times -2. That is 3 times -2 equals -6. So maxDP2 is -2. MinDP2 becomes min of -2 and maxDP1 times -2. That is 6 times -2 equals -12. So minDP2 is -12. Result stays 6, because max of 6 and -2 is 6. At I equals 3, x is 4, which is non-negative. MaxDP3 becomes max of 4 and maxDP2 times 4. That is -2 times 4 equals -8. So maxDP3 is 4. MinDP3 becomes minimum of 4 and minDP2 times 4. That is -12 times 4 equals -48. So minDP3 is -48. Result stays 6, because max of 6 and 4 is 6. We finish and return 6. The output is 6, and the expected is 6. They match, so solution 1 is correct for this test case. Now let's try to implement it using solution 2. We're defining a function called maxProduct that takes an array nums. We set curMax to num0. This tracks the maximum product of a subarray that must end at the current index. We set curmin to num0. This tracks the minimum product of a subarray that must end at the current index. This matters because a negative times a negative can become a big positive. We set result to num0. This stores the best product we've seen so far. Now we loop from I equals 1 to the end of the array. Inside the loop, we store the current number in x. If x is negative, multiplying by it will flip signs. So the current max and current min swap roles. That's why we swap curmax and curmin using a temporary variable tmp. Now we update curmax. We choose the better option. Either start fresh at x, or extend the previous product by doing curmax times x. So curmax becomes math.maxx, curmax times x. We also update curmin. We choose the smaller option. Either start fresh at x, or extend by doing curmin times x. So curmin becomes math.minx, curmin times x. Then we compare curmax with result. If curmax is larger, we update result. After the loop ends, we return result. Time complexity is O of n, because we scan the array once. Space complexity is O of 1, because we only use a few variables. Let's verify solution 2 for maximum product subarray. Input is nums equals -2, 0, -1. We start with curmax equals -2, curmin equals -2, result equals -2. At I equals 1, x is 0. 0 is not negative, so we do not swap. Curmax becomes max of 0 and -2 times 0, which is 0, so curmax becomes 0. Curmin becomes minimum of 0 and -2 times 0, which is 0, so curmin becomes 0. Now result becomes max of -2 and 0, so result becomes 0. At I equals 2, x is -1, which is negative, so we swap curmax and curmin. They are both 0, so swapping changes nothing. Curmax becomes max of -1 and 0 times -1, which is 0, so curmax becomes 0. Curmin becomes min of -1 and 0 times -1, which is 0, so curmin becomes -1. We compare curmax with result. Curmax is 0 and result is 0, so result stays 0. We finish the loop and return 0. The output is 0, and the expected is 0. They match, so solution 2 is correct for this test case. Let's recap maximum product subarray. This one is a great reminder that products behave very differently than sums, especially when negatives and zeros are involved. The goal is to find the contiguous subarray with the largest product. What makes it tricky is that one negative number can flip the sign and turn a weak product into a strong one, while a zero can wipe out the running chain and force a reset. So the challenge is managing those swings as you move through the array. Brute force would mean checking every subarray, which doesn't scale. The key insight is that because negatives can flip results, you can't track only the current best product, you also need the current worst product. A previous minimum, when multiplied by a negative, can become the next maximum, which is why tracking both values enables a clean single-pass solution. The structure uses 3 trackers: the global maximum product, the current maximum product ending at this position, and the current minimum product ending at this position. As we iterate, each number forces a choice: start fresh or extend the current chain. And when the number is negative, we swap the current max and min before updating. So sign flips are handled correctly. We implemented this successfully on LeetCode without errors by updating the running max and min at every step, accounting for sign reversals, and continuously updating the global maximum as the best product evolved through the array. LeetCode test cases confirmed correctness. For 2, 3, -2, 4, the algorithm correctly found the maximum product of 6. For -2, 0, -1, it correctly returned 0, showing that resets at 0 and tricky sign changes are handled reliably in linear time and constant space. The main lesson here is adaptability under changing conditions. By tracking both the maximum and minimum products as you go, you can handle negatives and zeros confidently, turning an unpredictable problem into a stable, efficient pattern you can reuse in other challenges.